Morning, everybody, and thank you for spending your time with me. My name's Peter Hunnaball. I've been with Flacked Woods, or what was Horticulture, since 1972. So I've done a few different things, including running laboratory and project teams. The purpose of this presentation is just really to make sure that we all understand what we're talking about in terms of fans in the same way. So we're all talking about the same language when you come to do any of the reprogrammed seminars later on. So what are we going to be looking at? I guess that's the thing to start with. And right, yeah, there we go. So basic principles of air movement when we talk about it applied to fans. Key air qualities and the units that we get involved with. The units I make quite a point of, because we always want to work in SI units. Measurements, how we might use the results, the characteristics of fans that you as a user would be interested in. Then we talk about power, how we size power, the sort of powers that we talk about. Then go and have a little look at all fan types. And the background then to the fan selector, the new fan selector, which enables you to select the fans with the knowledge that we're going to get. So, why does air flow? Like any fluid, air will naturally move from a high pressure area to a low pressure area. So if we create a differential pressure, we will get an airflow. And our fan creates a differential pressure, causing air movement. And how do we do that? Well, there's our lovely aerofoil fan, and if you're able to look closely at that model as it changes through the colours, you'll see that there's a compression above on the top of the blade and a stretch below. So then if we increase the angle, you can see that our compression's got even greater. And so when we increase the angle, we'll get a greater flow. Or if we speed the thing up, we'll get a greater flow. So, well, we know all about fans now, but we'll learn a little bit more. Let's talk about the key features of the airflow and what happens with the air. So velocity, it's the speed of the air past a fixed point. Lots and lots of different ways of describing that in terms of units, metric, imperial units. And there we go, velocity. But the one that we want to concentrate on is the SI unit. It's meters per second. That's our key unit. That's an important design feature. Anybody who's involved in conveying or drying, those sort of processes, velocity is a key design feature. But also, it can be a way of controlling the energy that's generated within the system. High velocity systems tend to have high pressures and therefore high energy usage. So what we quite often see in a specification is that we're not allowed to exceed a certain velocity, and that's seen as a way of controlling the pressure development. Right. The most important one in 99.9% of applications is the volume flow. If you've got a certain amount of air changes that you need to achieve within a space, then you will take the volume of that space, multiply it by the amount of air changes, and that gives the required volume flow. And that could be, again, lots and lots of different units, depending on the parts of the world you work from and your discipline. But the principal one will be in meters cubed per second that we will see. That's the common axis on our fan catalogues. And if we know what the velocity is in a duct and we know the area of a duct, we know what the volume flow is. So again, nice and straightforward. But that is the key factor that we need to have. So that's a couple of the key components. Let's look at the pressures involved, because that's very much about pressures when we're talking about fans. And the static pressure is is that reflects the resistance that the fan has to overcome to give the required volume flow. So, and that works equally in all directions at any point in a system. So, and that, so again, that's the work that the fan has to do. The units for that, pascals, newtons per meter squared. And if we know to get the static pressure, we'll take the total pressure of the fan, less the dynamic pressure. First time we've introduced that, but that will keep cropping up. And it all makes sense, really. If we're trying to push the same amount of air through a number of different systems, if we've got a small duct and it's very long, we go much higher frictional losses. If we shorten that duct, bigger diameter, we reduce the inlet and outlet losses and the frictional losses. And if we've got a very big duct for the same volume, then our frictional losses really come down. Just nothing more than common sense. So remember, the easy way to remember, of course, with the static pressure is once we've tied our balloon off, after we've blown it off, it's the static pressure that maintains that size. In a practical industrial sense, then this is a good example. So if we've digging our hole in the ground, or it's a mine or whatever it is, the people doing that work need to have fresh air delivered to where they're working. That might be several hundred meters inside the tunnel. So effectively what you put on it is a flexible duct, which is no different to a balloon almost. And the static pressure will maintain the shape of the duct while the air goes down it to be delivered to the workspace. So it's that's a very practical illustration. The next one is total pressure. The difference between total and static pressure is something I'd like you to come away from this presentation understanding, because it does make a big difference for fan selection. So the total pressure is the sum of dynamic and static pressure, in this case of a fan, but it could be anywhere in a duct system. The important thing is it becomes a measure of the energy level in the air. Units of pascals, per meter squared, and the total pressure is the static pressure plus the dynamic pressure. So once we know any two of the pressures, we can simply derive the third. And that is a characteristic of the fan that's in a system, but of the system as well. So just a reminder there. You'll have all this when you have your PDF copy of the presentation just to refer to. But one of the other important ones is our dynamic pressure can be calculated if we know what the density and the velocity is in the duct. There's a key principle in terms of how we can measure. So it's very interesting, all these pressures, but what's actually mean to us? But fans are described by the performance that it gives. Seems very obvious, but so total pressure, static pressure, dynamic pressure, that's really the basis of our aerodynamic performance. The test standards rely on measuring fan performance in a standardized test airway, and from that we can calculate performance curves. So if we understand those, how we measure pressures, especially at site, that helps to give us the best understanding and knowledge on how we measure fan performance. So in very simple terms, there's our fan, very nice long straight duct. It's working against this resistance here. So at this point where we want to measure the performance, remember, static pressure is equal in all directions. So if I measure that on a side tapping on the duct, measure that to atmosphere, the difference in the pressure gauge, used to be in water gauges because you'd have a U-tube with water in it, but now of course it's done electronically. That is the static pressure. remember that I said that the total pressure is the sum of the dynamic pressure and the static pressure. So in my duct, I've got my static pressure working equal in all directions, and I've got the airflow moving down, which if I put an open tube facing that air, that means I've accelerated that air to zero. So I've got the static pressure and the dynamic pressure. So again, if I put that across a gauge, I measure total pressure. So by putting total pressure on one side of a gauge, static pressure on the other, I measure the dynamic pressure. So simple things that we do. So how do we measure it? Well, the most common way to measure it is with this device called a pitot tube. A pitot tube has an open total pressure tube facing the air, and that's mounted within another tube that has static pressure tappings. So we measure directly the dynamic pressure. And the way, what you would do, if you could find a nice straight length of duct, you would measure in even spaces over that duct, or where we come to a circular duct, you do it in equal areas. So, and by averaging over those areas, you will then come up with a meaningful dynamic pressure, so we know what the volume flow is. Lots of different methods. People use hot wire anemometers and things, but probably consistently the most accurate measurement method at site is with a pitot tube. So we understand all about pressures now and doing some measurements. Let's think about the power side. So power in all of our lives, especially with the rising costs of power, has become very, very important. When we talk about fans and power, we talk about two specific powers. When we talk about safe and reliable installation, the first is a duty absorbed power. So that on our fan curve, we'll be looking at a little bit later, for any duty that will tell us what the absorbed power is. But also on that curve will tell us the maximum power that fan can absorb at that pitch angle. Very much as for axial flow fans, the pitch angle. For a centrifugal fan, that would be at a speed. So that's what we have. Those are the two powers. And as a policy, which we have always sized motors on peak power, unless there's a very specific need. This is a selection I've taken out of the fan selection software, and it's for just a normal 560 diameter fan. And my duty power, shaft power, is 5.4 kilowatts. My maximum shaft power, 6.5 kilowatts. So if I size that motor on the absorbed power plus 10%, that gives me 5.91 kilowatts. So what that means is if the pressure increased above 590 pascals, the motor would start to overload, right? Because we're starting to go above what the motor power is. That doesn't mean the motor is going to fail straight away, but what it does mean that motor will fail prematurely. So it's going to be, maybe 8 years instead of 20. I don't know. So the risk of sizing motors on absorbed power is that if the site installation is bad or the system calculation is wrong, the fan could fail prematurely. I mean, if it was to work at the very peak here, you'd start to get serious early failure. A good rule of thumb, which I've learned in many years of being a fan engineer, that every 10 degrees C that the motor works in increased temperature, you half the life of the motor. So you can see if you really start to overload it, you could end up with quite an early failure. And when we talk about power, this is the power that we talk about for the fan. The fan absorbed power is the power that comes out of the motor. particularly important when we have to calculate our performance against the energy related products, where we have to, that gives us an efficiency reflection of how the fan is working. So that's when we talk about the powers, what we need to drive the fans. There's no surprise that the motor efficiency is what we get out here over what we put in. So it's just a reminder, the power output from the motor on a direct drive fan is equal to the absorbed power. On a belt drive fan, as the power required at the shaft plus the drive losses. So let's have a little bit of a think about when we talk about these motor powers. If you go into a motor shop and buy a standard off-the-shelf motor, this is what you will have, IC411. So that is a motor with a cooling fan on the back. I'll just quickly go back. That's this. So that is a standard motor arrangement with a cooling fan. So it's fine, and we know what the output is. But that same motor, if we take the cooling fan off, that motor then becomes an integrated fan motor, so that the output of that motor can only be measured when it's fitted with a fan impeller on the shaft. That then becomes a different cooling. That's an IC418, and approximately 20% extra motor output can be gained by doing that. We're blowing a lot more air over the motor than you would get from a cooling fan. So that the important thing is that the temperature within the motor, the winding temperature, is maintained at the same level. So the temperature within the motor under this condition or under this condition would be the same. But what that does mean is that maybe you can get smaller motors in for the same power. That's good. So we understand that. Let's talk about efficiency. Said before, that's what you get out over what you put in. So with a fan efficiency, it's air power over the absorbed power at the shaft. This is where the beauty of the SI units. So if I know the volume flow in meters cubed per second times the total pressure in newtons per meter square, that breaks down Newton meters per second, which is watts. So you can look at a duty and know what the absorbed power is going to be. It's a very tidy way to look at that. So motor efficiency has become very, very important, and we've moved on significantly in the last 20 years, really. In June 2011, we were talking about IE2 motors as being just the general level. But then once we've had the legislation moved in to increase these MEPS, motor efficiency target figures, then that means that we've now moved on, and currently any standard motor has to be IE3 efficiency. When you've got an integrated fan motor, like with it's where the air is cooled from the air off the fan, then the rules change, because that is not a standard arrangement. But what it doesn't change is the fact that we have to build our fans to meet the legal energy related product requirements. So the efficiency level of the overall unit has to meet that, whether it's an integrated fan motor or a standard motor. Because when we talk about the ERP, we're talking about combined efficiencies. So this is a way of being able to drive down energy consumption globally. Quite simply, if you've got a fan efficiency of 80% and a motor efficiency of 90%, then that's our combined efficiency like that. So and then if you've got the, so we can look at the energy input for any global application. And that will, it's becoming harder and harder and harder all the time, the targets to meet that combined efficiency. Right, the other thing that will change how the fan operates is temperature and density. So fan curves and fan performances that you'll see generally are stated at a common reference point. And in Europe, it's 1.2 kilograms per meter cube. For the American market, it's slightly different, but very close. And that, by example, is 16 degrees C air, standard barometric pressure of 1013, and humidity 68%. So just a pretty standard sea level condition. But what does actually make a difference too? With the air density, you get a proportional change to temperature, and it's absolute temperature, so it's Kelvin. So the colder the air, the higher the density, the warmer the air, the lower the density. So if air changes from 16 to 50 C, that's the ratio between the two temperatures in absolute terms. So you can see our 273 plus 16, 273 plus 50. So then we get 0.895, roughly 0.9 factor, which applies to the density. So 0.9 times 1.2, the density is 1.08 kilograms. So if the importance of that is, if you're doing fan selection, is to know at what density your duties have been calculated at. Because if your density has been calculated at a low, if your duties have been calculated at a low density, we need to make sure we select the fans at that. And you can always model that within the software. So all of the things I'm telling you here all happen within the software. So the fan laws, and this is how it's affected by speed and density. So if we change the speed of a fan, we directly proportionally get a change in the volume flow. The pressure changes, so our pressure changes by the ratio of the speed squared and directly with density. And the power, because remember that power is volume times total pressure, change in speed cubed, but again, directly proportional with density. And so just that, the volume flow doesn't change with density, but pressure and power vary. And the other important thing to remember is that fans are a constant volume machine. So the lumps of air that we throw through our fan won't change no matter what the density is, but of course the mass flow will change. The mass flow being the volume times the density. Just worth remembering. So when we talk about the fan laws and how that works, that applies to systems as well. So if you're trying to push, if you're taking half of the volume through your system, the pressure goes down to a quarter. If you double the volume, it increases fourfold. So the fan duty is the point at which the system line that you've been calculating crosses the fan performance curve. So there's your system line. Sat down, worked all the duct resistances and things, and we've got at 6 units, we need 300 units of pressure. There's our fan tested in the laboratory, number of test points, which we then smooth and turn into a catalogue curve. We then plot our system line onto our fan curve, and we can see it's not a perfect match. In this case, we're probably getting 6.5 units at 350 units of pressure. But that is the point at which, if everything is accurately calculated, the fan would work. But it's important to remember that when we look at fans, we understand how the fan is installed, because a fan will be tested under all of these different conditions. The two most common are type A, which is without any duct, or type D, where we have duct on both sides. B is with a duct on the outlet, and C is with a duct on the inlet. If we look at that as a picture, then that's what we see. Then kind of showing a centrifugal fan. So there, type A, nothing on inlet or outlet. Type B, just a ducted outlet, type C, just a ducted inlet, and type D, the duct on inlet and outlet. So again, important, if you know how your fan is installed, always select the fan in that way. And that again sets up within the software of the program. But you know, you sometimes need to vary that duty. We can vary what the user has. We can have multiple fans, either in series or as multi-stage fans. Multi-stage fans rotate against each opposite directions. But in that case, we can't get more volume through that fan because they're one behind the other. But the pressure will increase. Or we could have two fans beside each other. So we get more volume flow, but the pressure development won't change. Or most commonly now, we can vary the speed of the fans. So how does that interact with a system line? So what I've done here is to take similar fans, and this is the single stage selection duty. So there's our single stage fans. I can put two fans in series, so two identical fans in series. I get an increase in pressure, but I only move from here to here in terms of volume flow. A two-stage fan, which is contra-rotating impellers, huge increase in pressure, but really not too much in terms of volume flow. Or this is my option for two fans in parallel, a significant increase in volume flow, but I'm getting close to this stall point on the curve, which I don't want to work at. So this is where I guess we start to see the logic of speed control by inverter drive. Because with my inverter drive, I stay on the same best position on the curve. Because all that happens is the curve shrinks. So this curve is, again, catalog curve at full speed, 2/3 and 1/3 speed. Look at the dramatic reduction in power. But we would recommend not to turn down the more than to 20% of speed. And that's really because the losses in the motor start to change. So hopefully there you can understand the logic of the SR units. So you've survived the first part. Let's talk about basic fan types. Lots and lots of different fans, from plate mounted fans, furnace fans, stainless steel food fans, material handling fans, standard air ventilation fans, variable pitch and motion fans, through to crenellated blades for noise reduction. And there's our latest in the family, which is the J&V fan that has a two-stage guide vane unit in it. All fans serve a purpose, and nobody has one fan that will do every duty. There'll always be a best fan for the best job. So let's look at the basic sorts of fans. The axial flow fan, the way I like to think of it is you can see through the axial flow fan. The air comes in and out on the same axis. We have an airfoil section that rotates to produce lift and therefore flow. And the geometry that we have will depend on how much pressure or volume we might get. Centrifugal fan, and most people who've got a hairdryer in their house own a centrifugal fan. There it is. It's where the air comes in and comes out at right angles. It's a smaller inlet compared to the axial flow fan. And the last one is the mixed flow fan, which starts to flow tangentially, then is straightened out with guide vanes to an axial discharge. So you think, well, why do we need that? We look at sort of a notional arrangement of duties. The centrifugal fan is very good in terms of pressure, but has restrictions in terms of volume flow, mainly because you've got to get the air into the fan. The mixed flow fan is a little bit of a hybrid of the centrifugal and axial flow fan. So again, good, not bad pressure, and a little bit more volume because it's much closer to an axial in terms of the inlet conditions than the axial flow fan. Axial flow fans are all about volume flow, some pressure development, and you can see that for this area of duty, all fans can compete. But there are areas where each fan individually is the best fan. So just have that in the back of your mind. But if we said, right, I've got 10 kilowatts of power, what can I have for 10 kilowatts? This is something that the Sibsy team did and did a very simple comparison of what you'd get in terms of volume, flow and pressure. Did it take for your 10 kilowatts? And you can see it's a radial bladed centrifuge where lots and lots of pressure, not very much volume. And there's our axial flow fan, nice lot of volume, but a medium degree of pressure. Right, the axial flow fan, in principle, a very simple product. And a round duct is something that sounds very easy to say, but it's not always easy to make. When you try and roll a piece of steel, even with flanges on it, it has a tendency to want to try and turn itself into an egg shape almost. So the skill is in the manufacture, because the rounder you can make that duct, the better. So we've got our motor mounting arrangement, in this case a platform because of a foot mounted motor, but most of the time we would have the motor supported on 4 pads because it's aerodynamically the best. You take the cables from the motor out to a terminal box on the outside of the fan, but the most important part is the impeller, because the impeller is where all of the technology is within an axial flow fan. That defines how efficient or otherwise we do, how much pressure we can make. That's an important combination. And this is a long case fan where the casing covers the impeller and the motor. Nothing sticks out. This is a short case fan. So in this case, the motor sticks out of the fan casing. These are often used on OEM type arrangements or at the end of systems. The fully ducted fans, the long case fans, tend to go into fully ducted systems. Right, plate mounted fans. These are people have been used to seeing these in the walls of barns and places like that, just generally used for that, but also for the heat transfer market. We have a plate mounted fan where we've got our fan. It's a type A installation, no duct inlet or outlet. And the fans are made so you design specifically for the efficiency of that arrangement to try and make it the best that you can. We have specific ways of mounting the fans. So globally, this description of the fans applies to all axial flow fans. And this is the standard. Type B, horizontal mounted is the standard. And the easy way to remember that for me has always been that the air comes to the impeller before the motor. Type A, it's after the motor. Okay. Form B is on average about 3 dB quieter, and that makes sense because there's no turbulence created when the air goes over the mounting to get to the impeller. It would be form A up, A down, B up, B down. So once you memorize that, and worth knowing, and that's important, that is an important thing to say. There is a difference in the construction sometimes if we have a vertical fan compared to a horizontal fan. I spoke about multi-stage fans, and here's the illustration of that. Impellers that rotate in other directions, up to 2.7 times the single fan pressure, efficiencies up to 85%. One of the other nice things though is that the air is reduced swirl, so there's less rotating corkscrewing air after a 2-stage fan compared to a single stage. And there's my plot straight from the fan selection software, just demonstrating the difference that we get. Okay. Centrifugal fans. So you can see with a centrifugal fan, the air enters into the eye of the impeller, it's then rotated and comes out in this snail shape, what we call a scroll, to the fan discharge. So they're the key components, if you like. That can be directly mounted onto the end of a motor. What very commonly used in industrial applications, where maybe on the back of the arrangement where the impeller is supported, there'd be a coolant fan. If you've got very high temperatures, the temperature enters the shaft. That helps to dissipate that so it doesn't get to the bearings. You have things like flexible connectors, anti-vibration mounts, and in this case, a motor on a slide rail, which means it's belt driven, often specified for industrial use so that people can actually change the motor without taking the fan to pieces. Different sorts of centrifugal fans. This is a forward curve centrifugal fan. This is the sort you've got in your hairdryer, but one of the problems is it's probably the lowest efficiency. When the ERP regulations came in, these suffered in the same way some of the propeller fans did. But the thing you have to be careful of is if you open the door or let the system resistance drop, the power will shoot up. So it's an overloading power characteristic. These are what people recognise as industrial fans, robust construction. The blades are radial, so they're coming straight out like that. Very good when you've got anything that's got dirty air, because they naturally self-cleaning, because there's nothing for the dirt to stick to. Not so efficient, but designed for a purpose, for harsh applications. And the even heavier duty version of that would have blades that you can replace. So if you're handling abrasive dusts and things like that, you need to have something where you can replace the blades if they become worn. Again, not highly efficient, but highly effective. Self-cleaning blades. Any radial blade is self-cleaning. Now we start to get to the more commonly seen centrifugal blades, what we call a backward incline. So it inclines backwards or the flow is forward. Can handle some contamination because you're fabricating these from steel, and as we all know, some very complex steel combinations that you can get in terms of strength. Reasonable efficiency, not the most efficient in terms of use for HVAC, but a commonly used fan. The one that's most common is the backward curved blade. So you can see that by curving the blade backwards, you reduce the losses, get some very good efficiencies. This is what it looks like in practical terms of a swing out arrangement, but probably the most common impeller design for use in HVAC. And that, you know, and we see them. So this would be, I think this is a 5 megawatt impeller used for an ID fan on a power station. So that's the one extreme. But the most common use now probably of that design is in plug fans. Plug fans have become very dominant in air handling unit and box design systems, where you take the fan and you pressurize a box and then take your air from that box. Become very, 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 very common because it's nice and simple to make and effective. The Rolls-Royce centrifugal fan market is really the backward curved aerofoil section blade. But you can see that if you're going to have an aerofoil section, you've got to fabricate that. If you fabricate it and you have the welded construction, you must allow the gases to get out. So while the efficiencies can be phenomenally good, it's complex to manufacture, and you can only use it in clean air applications. So you'd only see it in very high specification applications. The mixed flow fan has a little bit more of an interesting history. This shows one of the flat woods mixed flow fans. They were developed specifically for the North Sea oil platform market, because these fans run very, very quickly. They have a high volume and pressure characteristic, but they're extremely noisy, as any fan that's run at very high speed will be. But when your construction restraints are on the square meterage of the floor, then the smallest fan that you can possibly get to do duty has some advantage. But this shows the arrangement really, where you have an impeller that then feeds the air into a guide vane arrangement. Efficiencies are okay, but they do suffer now. This fan that was originally made then would not be acceptable in terms of ERP as a fan alone. It would be as a specialised fan arrangement, but not for ERP. Right, if we got the different construction details, how can we mount it? 99.9% of axial flow fans will be direct drive. So we have the motor and the impeller bolted directly. One of the disadvantages is that you need to, for a major overhaul, better to remove it from the system. And so that then is not preferred by industrial users. So belt drive, where you have the impeller driven by a belt assembly, has some advantages in terms of a low repair time if you've got a motor failure, but you have an additional set of bearings, and probably at least 80% of failures would be due to bearings, so that becomes a little bit questionable. Plus you have the drive loss, which can be anything from 5, maybe a little bit less than that, up to 25% if it's a small fan of the drive power. So ERP compliance can be complicated, but undoubtedly preferred for industrial processes. The last one would be a coupling drive. The problem with that is they're not easy to set up and they're complex to maintain. So unless there's a real advantage, effectively it's the same as a direct drive because you've got no other drive losses, but would be avoided as hard to make. What are the other characteristics of the fans? If you look down on the fan from above, a centrifugal fan has a large footprint, and I say that because the air, the duct coming out and the duct going in are not in line. You've got to be able to accommodate that fan in your space available. But you can change the motor with the fan in place, get very good efficiencies, all the different coupling noises, but low frequency noises are characteristic you have to be careful of. If you stand a centrifugal fan beside an axial flow fan for the same duty, you will say, "Ooh, the axial flow fan is much more noisy." But the characteristic of the centrifugal fan is low frequency noise. And low frequency noise is difficult and expensive to get rid of. So be cautious. It's a fixed, it's a fixed geometry fan, which means that to change the duty, you have to change the speed. But medium volumes, high pressures. But one of the real advantages, and you can see why for process industries, is you can make it capable of operating at very high temperatures permanently. Because that's whatever complicated material you want to make it out of, you can do that with careful design. So what's the axial fan? Axial fan's got a small footprint. I say that because you've got an 800mm duct that runs through your factory, but you find you need to boost the air a little bit more. You can cut out the section, put 2 flanges on and bolt it in. Easy to install and remove because there's no change of duct direction. The duct and the air goes in the same direction. Get efficiencies up to just over 85%. You can have the different arrangements, but we specialise in direct drive fans because of the most efficient and low loss installation. High frequency noise. So when I said before about you stand the 2 fans beside each other and listen to the 2, the axial is much noisier, but if you understand the characteristics of noise attenuators, that's almost matches that noise profile. So it's easy to attenuate. And you can put a circular line duct silencer on any axial flow and it'll take out 10 dB either side. It's adjustable geometry, so principally we adjust the angle to get the duty that we want, but we also know that we can adjust the speed. It's all about volume and medium pressures, but it does have limited operating temperatures, because our fans in particular, and most axial flow fans, are from cast aluminium. Aluminium weakens with temperature, so we have to understand that. So when we have fans that are made for HT or for ATEX, all standards that we have to conform with, they all have their own specific requirements and limitations. And for example, you will always have to have increased tip gaps with ATEX and high temperature fans, which lowers the pressure development. But just a couple of things to sort of finish up with, really. Stall or something I'd like you to understand. All fans have potential stall. Centrifugal fans, this is the lower end of the characteristic. So I normally you'll see characteristics start off here somewhere. With an axial flow fan, that's at the higher end of the characteristic. And so typical the curves cut off somewhere like this. What does that mean? Well, it's exaggeration, of course, but it's increased noise, low level. You can hear that. If you put your hand in the air after a fan, under normal circumstances, it's like a smooth force. When it's installed, you'll get severe pulsation. If you look at the absorbed power, you'll see that it fluctuates. So, be careful, because that probably is the cause of more failures than anything else in fan use. That will be different modes of fans. With our fan product range, we know how fast you can run the impellers forward, we know how fast you can run them in reverse, and we know how fast you can run them in the stall. So just make sure you ask if you've got a dedicated requirement. And the last thing I'd like to finish with is just this difference on total and static pressure. As a company, we will always assume, unless we're told otherwise, when you ask us for a pressure, that's static pressure. Because if we don't, and this is an example where it was actually a static pressure duty, but was selected as a total pressure. And so what I've done, this is the static pressure curve. This is the curve for the same fan selected in total pressure. And what I've done is to remove the dynamic pressure, so I have that fan dynamic curve. So that would mean is that we'd be on a system line, we'd be 6% down. But if you had a definite requirement at that volume, you'd be 70 pascals down. So it depends how important that is to your system. And the way you know if it's an atmosphere to atmosphere calculation is that there will be, for total pressure, a stated diameter somewhere in that calculation. So always ask if you're not clear, because if we decided, for example, that we select in total always, then that's the sort of error you might get at site if it's a static pressure duty. So just always be clear about what your duty is. With that, I'll say thank you for your time.